Good morning, guys. Today we're going to wrap up our unit on explicitly confidence intervals. This isn't the last time we'll work with confidence intervals, but just on the basic mechanics of confidence intervals. So today we're going to look at estimating a population mean using confidence intervals. So here's our setup for today. The principal wants the school to average a 21 on the ACT this year. To best prepare for the ACT boot camp, he needs an estimate of the school's current ACT average. 3 different committees conducted studies, but they need us to calculate the 95% confidence intervals for estimating the mean RHS score. So they've got the data, they want us to use them to estimate. So study 1, we had a simple random sample of juniors, and we just asked these 10 students their scores. We also looked up the state or the national standard deviation and found it to be 4.8 points. Study 2, we have 25 RHS juniors, and we know the mean is 20.4. And this group looked up the statewide standard deviation, it's 5.2. And they also found that ACT is usually normally distributed. And then in study 3, we had 45 RHS juniors. That group had an average ACT of 20.2, and the standard deviation for that group was 5.1. So first thing we know we always have to do whenever we're doing inference is to check conditions. So the 3 conditions that we're always looking for, we're looking for randomness. 2 ways we can get randomness. Either having random samples or random assignment. So it needs some type of randomness involved in the study. Number 2 is independence. It's the same independence we've looked for before. Either 10% condition, where the sample is less than 10% of the population, or we can reasonably say that these individuals would be independent. One person's response or measurement should not really be tied to or reflect other individuals' responses or measurements. And then normality of the sampling distribution. So normality just tells us what type of calculations we're allowed to use, what type of approximations we're allowed to make. So 3 different ways. We talked about 2 of these before. We're going to kind of expand on a third possible. 1, the population is normal. Remember with means, when your sample size is small, your sampling distribution takes on the same shape as your population. So if your population is already normal, then having a small sample is not an issue. Now, if our population is not normal, then we've got to have other things come along. So that's where large sample condition. If I've got at least a sample of size 30, it doesn't matter what the population looks like from a shape standpoint, the sampling distribution is going to be approaching that approximately normal shape. So large samples, n greater than or equal to 30, we're good on normality. Well, what if we have a small sample, so we failed here, but we don't know what the population looks like? Well, if that's the case, then we just sketch the graph. Because we know that our sample should resemble our population if it's a good random representative sample. So if we have a good random representative sample, then we can assume, that's what we're talking about, conditions or assumption, then we can assume the sample is going to look like the population. So if we see no strong skewness, no outliers in the sample, then we can assume that there's also no strong skewness, no outliers in the population. So that's what we do. Quick dot plot or quick box plot to look for strong skewness or outliers. And when we say strong skewness, we're talking really obvious outliers or really obviously a lot of data clumped on one side and then drags out to the other. So those are the 3 conditions that we're always going to be looking for. With means, it's a little bit different because we're dealing with actual sample size instead of counting like we did proportion, successes, and failures. All right, let's go over and look at how maybe some specifics on calculating confidence intervals for means. So let's look at the details of estimating population means for confidence intervals. So we know all confidence intervals are built the same way. Point estimate plus or minus the margin of error, which consists of our critical value and the standard deviation of the statistic. Means have one of 2 things that can happen. And it goes back to what we know about the population. So if we know the population standard deviation, if we know sigma x, nothing changes. We're going to do the same things we did with proportions. We're going to use our point estimate, which in this case is the sample mean. We're going to use critical z's, which we get from inverse norm. Remember, how do we inverse norm? You need area, mean, standard deviation. Well, mean and standard deviation on anything with z's is your standard normal mean of 0 and standard deviation of 1. And remember, area was that left side tail, so 1 minus confidence level divided by 2. So 90% confidence level, my area is going to be 0.05, because 1 minus 0.90 divided by 2 is 0.05, and so on. And then standard deviation of the statistic. Only difference now, we're doing standard deviation of mean instead of standard deviation of the proportion. So standard deviation of x over square root of n. So population standard deviation divided by square root of sample size. So we're just doing standard deviation of x bar. That's if we know the population standard deviation. Well, as with a lot of our studies, we walk in not knowing anything about the population. If I don't know anything about the population, then I need to just build samples and try to get a picture from there. So option B, if we don't know about population standard deviation, we're going to use sample standard deviation. This is very similar to what we did with proportions, because with proportions, if we didn't know population, the population probability, we just use the sample probability or sample proportion. Same thing here. If I don't know population data, I've got to go with sample data. So my standard deviation becomes a standard error. With means, we get one additional change though. We don't just change to standard error, we also change from Z distributions to T distributions. All right, so what is a T distribution? A T distribution, if you'll notice, looks like a fatter on the ends version of a normal distribution. All it's doing is just saying, all right, we're not as good because we're working with a sample instead of the population. So since we're not as strong, let's put the probability of being out there in those extreme areas, let's make that a little more likely to occur. So we want to just put a little more, we have to have a little more strength to what we're looking at to get really, really extreme. So again, we're just kind of hedging our bets whenever we're basing things off of sample data. So that's what a T distribution looks like. Now T distribution is going to change shape depending on what that sample size is. So notice here in the green where I've got my sample of size 3, it just barely gets up and then it's really, really fat. There's a lot of samples, out of all possible samples, there are a lot of samples that happen out in those extreme regions. So it's a high probability that we could be out there. But as I've got n equals 30, that's this purple line, my T distribution is going to get a lot steeper. It's going to get narrower on the tail, skinnier on the tail. It's going to push more towards the middle. So it's going to do more of approaching like this black curve, that normal curve. So large samples are going to, again, give us something that looks, even if we're having to use a T distribution, something that looks closer and closer to a normal. So the larger your sample, the closer your T values and your Z values will be to each other, but there's still going to be a slight difference there. Now, how do we actually calculate those T values? We're going to go inverse T. We're still going to the distribution menu, just like we did with normal distribution. So whether it's a normal distribution, binomial distribution, geometric distribution, or a T distribution, and later we'll get in and do chi-squared distributions. No matter what type of distribution, on our calculator, it's going to come off that distribution menu. So this is where it's very similar to normal distributions. If I need a value, I do the inverse. If I need a probability or an area, I'm going to do the CDA. So to get a critical Z, I do inverse norm. To get a critical T, I'm going to use inverse T. So with inverse T, it's going to ask for 2 values. And so instead of asking for area mean and standard deviation, like our norms do, our T's only ask for area and then DF. So we've got to kind of figure out what DF is. Well, area is no different. It's that left tail area. So it's still going to be 1 minus confidence level. It's a CL, confidence level, all over 2. DF is known as the degrees of freedom. And as we go forward, we're going to learn lots of degrees of freedom. We're going to have degrees of freedom on T distributions, on some chi-square distributions, and then we're going to have different types of chi-square tests. So they'll have different degrees of freedom. We'll have degrees of freedom with some quantitative, some other quantitative data that we work with, some bivariate stuff. So lots of different degrees of freedom involved. So we've got to kind of distinguish between the two. But the idea is you're looking at, I have all these values I can work with, and then how many extra variables and stuff am I estimating in there. So we'll talk more in detail about where these degrees of freedom, I've got a video and I'll show you all that kind of, I think, visually demonstrates that really well. So degrees of freedom for us right now is just sample size minus 1. And sample size minus 1. It's really just telling your calculator which T distribution I need to grab. So N minus 1 is degrees of freedom, area is 1 minus confidence level over 2. Once you've got that, you'll get a critical t value, and then we'll just type in our standard error into our confidence interval formulas. Standard error is just sample standard deviation over square root of n. And we'll pull up an example here in a minute where we'll actually key in one of these into the calculator and get the have to get that critical t. Now, if we were going the other direction, because we may have one of those later, where we have the critical t values and we need the area for some reason, that would be a TCDF situation. Just like given the z scores, we do normal CDF. If I'm given the t scores, then I would do TCDF. But let's jump in and actually talk about these 3 studies. All right, now if we're going to kind of analyze these 3 studies and use them to get a good estimate for our population mean, our average ACT score for the school, first thing we need to do is check conditions. So what I'd like you guys to do is pause the video right here. I want you to kind of go through and check conditions on all 3 of those studies. Let's see what you guys come up with. Hopefully your conditions come out looking like this. So let's go through them. First off, randomness condition. In study 1, did we have randomness? Yes, it quotes standard simple random sample of RHS juniors. That meets our randomness condition. Second condition, independence. Did we have independence? We look for 10% condition. Well, 10 RHS juniors is less than 10% of all RHS juniors, about 500 juniors that we're looking at. And then normality. So if we're kind of going through the list on normality, do we know about the population here? No. Do we have a large sample here? No. So we're going to go to that third option, which was check for strong skewness and outliers. So checking for strong skewness and outliers, just did a quick dot plot of those scores, 14, 16, 17, 18, 18, 21, 21, 24, 26, 31. So quick sketch of them. You could do it with a box plot. They're usually pretty easy to pick up too. And then you get about like that. Maybe there's a little skewness out here to the right, maybe. But it looks like it's fairly, again, no strong skewness, no outliers. We're talking about very obvious skewness. So everything clustered around 15, 16, 17, and then another score all the way up here. This one looks like it's got a little bit on the left, a little peak in the middle, and then a few on the right. So I feel, confident there saying no strong skewness, no outlier. So study 1, we're good to go on that one. Let's talk study 2. Did we meet randomness condition? Simple random sample of 25 RHS juniors, good to go there. Did we meet independence? So 10% condition. Well, 25 RHS juniors is less than 10% of all RHS juniors. And then normality. So first off, check for the population. Well, in this one, it tells us ACT scores are typically normally distributed. So we know the population, according to this group, that is normally distributed, so the small sample size of 25 doesn't really hurt us. So we're good there. So study 3, let's check the conditions. Randomness, simple random sample, 45 RHS juniors, good there. 45 RHS juniors is less than 10% of all juniors, so we've met 10% condition for that second group. Remember, we got about 500, so really as long as we were under 50 or so, we were good. And then normality, so we don't know what the population looks like according to this group, but we did have a large sample. We had at least 30. So large sample condition was met because 45 juniors is greater than or equal to 30. So all 3 of these studies are have met conditions. So it means we can proceed with checking through and estimating, using these studies to estimate what's going on school-wide as far as ACT. So let's get in, let's start working with it. So in study 1, I want to set up my confidence interval. So I need my mean, I need my critical value, and I need my standard deviation of my statistic or my variability, measure variability right there. But remember, we've got conditions with means. I don't know if I need the Z or the T. So I need to go back and look at my study and decide, did they give me Z or did they give me a population information or sample information? Because if we remember, when I know what's going on in the population, I can use Z and standard deviation, but if I don't, I've got to use T and standard error. So if we'll look down here, in number 1, it says standard deviation, looked up standard deviation nationally. So nationally would be a population. It's not just those 10 students that they talked to. we're actually looking at population data. So in this case, we know sigma x, so that means we use critical z. So I'm going to be able to use critical z, and I'm going to be able to put standard deviation x over square root of n. So we're ready to go on this. So going through this one, first thing I need is the mean. So if I took all of these numbers and throw them in the calculator, average them up, I believe it comes to 20.2. Critical z, so if I'm grabbing my calculator, I'm going to do my inverse norm. So inverse norm, 1 minus my 0.95. Remember, that was the confidence level I think we were going with, was 95% confidence is what they told us to use down there in these requests. So 1 minus 0.95 over 2, that's going to be my area. Mean is 0, standard deviation is 1. So we do all that stuff, and we're going to get 1.96. And then we take the standard deviation that they gave us, 6.8 over our square root of 10 students. So got our critical z, got our standard deviation of our statistic. So our confidence interval ends up being 20.2 plus or minus 3.0. 20.2 plus or minus 3.0. So that's one way we could write the 95% confidence interval, or we could write it in interval notation. So it'd be 17.2 up to 23.2. So how do we interpret that? We are 95% confident that the true average ACT score for Riverdale juniors is somewhere between 17.2 and a 23.2. Let's go into study 2. Actually, we're going to pause right here. I want you guys to try to do study 2 now. So pause the video and see if you can come up with the confidence interval using study 2's information to estimate what's going on ACT score-wise for the school on average. And hopefully you got this. Okay, so let's see how you guys got this. So first you acknowledged that we know population standard deviation. So when we go back and look at the question, at the prompt, they tell us right here, they looked up the statewide standard deviation, okay, and got a 5.2. They looked up the statewide standard deviation. So that is a population standard deviation that they looked up. So that's why we can actually work with Z in this case. So it's going to be the same setup as the one before. Sample mean plus critical Z times standard deviation of X bar. So 20.4 was the average they gave us. Again, 95% Z's are always going to be 1.96 no matter what we're doing. 95% the critical value for 95% confidence interval with critical Z's is going to be 1.96. And then statewide, it's 5.2 over the square root of our sample size of 25. And we get this confidence interval. So again, we are 95% confident based on this study that the true average ACT score for Riverdale students is somewhere between an 18.4 and a 22.4. All right, now let's look at the last one. So in this last one, what type of standard deviation did they give us? Well, when we read through the problem, we've got the 45 juniors. The average for those 45 was 20.2, and the standard deviation for those 45 was a 5.1. So on this one, they didn't tell us what's going on with the population. They told us only about that group. So for this one, we don't know sigma x, so that means we're going to have to use critical t instead of critical z. Okay, so we're going to need critical t, and instead of standard deviation of the statistic, we're going to do standard error of the statistic. So sample standard deviation over square root of it. All right, so let's jump in and see if we can get this critical t. We know the mean already. What was the mean on that one? 20.2? Yeah, I think that one was 20.2 as well. Oh, that was off. This was, sorry guys, this was 20.6. And a couple of my samples off from each other. Okay, so this one, the mean is going to be 20.2. plus or minus, and we need to get this critical T. So we're going to go in, do inverse T. They're going to ask us for two things, area and df, which is degrees of freedom. So area is the same area we did on the z's, 1 minus 0.95 over 2, and then degrees of freedom is sample size minus 1. What's my sample size? 45 students minus 1. So on my calculator, in the inverse T, you can see clearly I just typed in 1 minus 0.95 over 2, and then my degrees of freedom I typed in 40. So I'm not doing any simple, I'm just typing in what it asks for. I don't have to do any simplifying or mental math or anything. And when we go through and paste that and hit enter, we can see that we get a negative 2.02. We've talked before how it's built in plus or minus. So we get 2.02. Very, very close to the 1.96, but a little bit larger. That's what we would expect for T critical values. They should be a little bit bigger than the corresponding Z critical values because we're trying to get a little bit wider. We're trying to loosen those estimates just a little bit because we're having to base it off sample data. Then we had the standard deviation, which I believe was 5.1 over square root of our 45 students. And we end up with 20.2 plus or minus 1.5. So that ends up giving us the confidence interval that we're looking for, which when you back that up, what's that, 18.7 up to 21.7. So this is our 95% confidence interval. So in this one, we're 95% confident that the true mean is somewhere between 18.7 and 21.7. All right, so now let's talk about using this to answer our question. All right, what's the point of getting all those estimates? We want to know if ACT Bootcamp is going to be useful. So if we found that ACT Bootcamp usually boasts things on average 2.5 points, are any of these studies enough evidence to say, yeah, this bootcamp is going to be good enough, we don't need to go in and get anything more extensive or more involved or anything like that? What we usually do should be good to go. So what we end up wanting is our pre-bootcamp estimates and then our post-bootcamp estimates. So pre-bootcamp, where's the school sitting? Well, in study 1, they're sitting somewhere between a 17.6 and a 23.6. In study 2, we're somewhere between an 18.4 and a 22.4. And then in study 3, we're sitting around 18.7 to 21.7. So how would I figure out what I look like post bootcamp? How would I figure out if we go up on average 2.5, where do we expect to be? Well, it's just as simple as adding, because these are estimates of the average, just adding 2.5 to each of those. So if I were to do that, add 2.5 to this guy right here, you get 19, you get 20.1 up to 26.1. Here, if we're going to add 2.5, that's going to give us 20.9 up to 24.9. And then on the last one, if we added 2.5 to that, that'd be 21.2 up to 23.2. So just taking them one at a time. Does this give us confidence that even after boot camp, then the school average is going to be above 21? Well, since we have plausible values that say the school average could still reasonably, we're 95% confident that the school average could still reasonably be below 21, then I would dump that one. That one's no good. So that study doesn't back it up for us. Study 2. Well, even this one right here, we had a lot of it above 25, but there's still a chance that that school average is not going to be above 21. It could still be a 20.9. It could be anything, but we're just saying that based off this interval. So that one misses. Well, in this third one, notice how the lower boundary is above 21.2. So the entire interval the entire interval exceeds 21. So that tells us that we are 95% confident that the school average after boot camp should be somewhere between a 21 and a 20, or 21.2 and 23.2. So that third study seems to be good evidence that, yeah, we're pretty good in where we're at and how far, with considering how far we need to get to. Now, as far as which one we would go with and all that stuff, that's for another day. But right now, we're just trying to show how to build the confidence intervals and compare them to a certain target value. Now let's talk about affecting margin of error. So affecting margin of error is very similar to what we did with the means or with the proportions. We're going to affect them pretty much the same way. Now, the limitations we get on affecting margin of error come from the limitations that we have with our t-distributions. So we know that if I'm going to estimate margin of error equals critical value. So let's say that we don't know anything. We went with a critical value of t times standard deviation over square root of it. So if I was going to try to mess with my confidence level, like we did with our, proportions, when we use the TCDF function, because that's what we would be doing right here, picking a confidence level and doing a TCDF. Our TCDF is going to be kind of based on needing to know, or our inverse T is going to be based on needing to know certain things like our standard deviations, our degrees of freedom and stuff like that. So we don't typically work in this direction where we're working with critical T's. When we deal with means, we're always going to be given the population standard deviation. This is going to be what we're given, and we're going to focus more on critical Z's in that case. Okay? So we're going to be focused on situations where we're given population information and we're going to do critical Z. So if we want to solve this thing, we're always going to be solving for sample size. And we like sample size, messing with sample size anyways, because I don't really want to weaken my estimate, right? If I want to get a much tighter thing, I've got to be less confident. I'd prefer to just go talk to more people. So margin of error. In this situation right here, we want to come up with a margin of error of 1, and they've told me that my standard deviation is 4.9. So margin of error of 1. We're going to do critical value of 90%, or sorry, confidence level of 90%. So going back in, inverse norm right here, okay? Inverse norm right here, we know that we should get 1.64, correct? 1 minus confidence level over 2, mean of 0, standard deviation of 1. If we plug in what we know, so we're looking for a certain sample size. We know our standard deviation is 4.9. And then it's just algebra at that point, right? Divide by 1.64, cross multiply and divide, square both sides, divide, all that good stuff. So we can see that through algebra, n comes out to equal 64.57. So we know that obviously you can't have 57 hundredths of a person, so we need n to equal 65. Why did we round up? Well, you guys are thinking it's because we were both being a half, but no, we remember that for sample size, always round up. For sample size, we're going to always round up, regardless of what that decimal is. Because if I round it down, give me smaller, give me a bigger number here, and we would exceed the 1. We're trying to be 1 or closer. Okay, so means had a lot of stuff thrown at you, so just kind of a quick recap. When you're checking for normality, you can have a normal population, you can have a large sample, or you can see no strong skewness or outliers in a quick sketch of the sample. When getting your critical value, if you know population standard deviation, then you're going to do critical Z, and you're going to use standard deviation of the statistic. If you don't know population standard deviation, then you're going to have to use critical T and then standard error of the statistic. Critical T needs two pieces of information from inverse T. It needs the area and it needs the degrees of freedom. And degrees of freedom is nothing more than sample size minus 1. Okay, so that's it for means. We'll get into class, we'll practice these and get a lot of reps with them, because it's just getting your hands in this stuff, and you'll see that it's a lot of stuff right now, a lot of stuff kind of keeps straight, but from a mechanics standpoint, it's not much at all. All right, that's it, and I will see you guys in class tomorrow.